This video is for 10 number 11, more on logistic differential equations. And start off with a brief review here. In exponential growth, we assume that the rate of increase or decrease of a population at any time t is directly proportional to that population. In other words, dp dt is equal to kp. However, in many populations, the growth levels off and approaches a limiting number L, the carrying capacity, because of limited resources. In this situation, the rate of increase or decrease is directly proportional to both P and L minus P. This type of growth is called logistic growth, and it's modeled by this differential equation. And if you find the second derivative, you can find out important facts about the time when P is growing the fastest. So it covers similar topics to the last lesson, but we're going to go ahead and look at the second derivative and at a case when the logistic function is actually decreasing, which we did not discuss last class. So first it is to rewrite dp dt. So we have the population P of t of fish in a lake satisfies the logistic differential equation of dp dt is equal to 3p minus p squared over 6,000, where t is measured in years. So this differential equation is a logistic differential equation, but it's not written in this common form, and I think it's easier to analyze if you take the time to rewrite it in the form such that there is a 1 here, so that the equation is in factored form with a 1 as the leading term in the parentheses. So if we just take dp dt and factor a 3p out in front, then this will be 1 minus, and if we take the p out of this, there'll just be a p left on top. And then by factoring a 3 out, we are essentially dividing this by 3, so the 6,000 turns to 18,000. And you can double check that by just distributing this back through here. You can see that if you had a 3 on the numerator of this, that 3 over 18,000 would equal 6,000 in the denominator. So when the differential equation is in this form, you should be able to identify the limit of the solution to the differential equation. So P of t is the solution to dp dt. And we could find the solution by having memorized the equation we were working with last class, or we could try to solve this differential equation, but it's not necessary in order to answer all the following questions about it. We just know that P of t is the solution, but we don't actually have to find the solution. So if we did find the solution, though, what would be the value of the limit? And the value of the limit would just be the carrying capacity. And you can see the carrying capacity in this function. And so the value of this limit is 18,000. And this is called the carrying capacity. So if we take this differential equation and solve it equal to 0 and make a sign chart to interpret the results. So let's take our 3p, 1 minus p over 18,000, and set it equal to 0. Then the solutions are when p equals 0 or p equals 18,000. And so if we make a sign chart of that, only care about time values greater than 0. We'll say that these are in thousands, so this will be 18, meaning the 18,000. And this is the graph of the sign chart for p prime. Notice that these are p values, the population values, not time values like they normally are. If you substitute in a p value that's between 0 and 18,000, then I guess we could go ahead and put 18,000 there. So let's say we put in 9,000, then 1 minus 9,000 over 18,000 would be 1 minus a half. That would be positive. This would be positive. So when the population values are between 0 and 18,000, then the population is increasing. And when the population are greater than 18,000, say 20,000, 3 times 20,000 would be positive, but 1 minus 20 over 18, this would be bigger than 1, and so this would be negative, meaning that if the population was greater than 18,000, then the population is decreasing. So that is a new situation for us, and I think we should stop and look at these graphs. Actually, let's look at it on, let's look at it on those graphs. So this is scaled in thousands, and we're going to try to make a graph of P of t, even though we don't have the function for P of t. We do know that in this case the initial value is 4,000, so that would be here. And we know that the carrying capacity is 18,000, so that would be here. And we know that the function is logistic. Don't know much about what's going on the time axis, so we're just going to sketch. We're just going to make a sketch, and we don't know exactly what it's going to look like, what the rate of increase is, but we're just going to do something like that. And this is the case where as long as the population is between 0 and 18, then it is increasing. This part over here, let's go through and kind of see these other cases. So if the population, instead of being at 4,000, starts at 10,000, we would be here. The 18 is there. And let's wait a second to draw this graph, but let's come over to this graph here where the initial population is 22,000 and the horizontal asymptote, the carrying capacity, is still 18. And what happens in this case is, say you have this lake that the fish are put into, and the carrying capacity, the environment can only support a population of 18,000 fish, but 22,000 were initially put into the lake. Then what happens is that the population ends up going down toward the carrying capacity. And that's why this sign chart has a negative here. So if the population is above 20,000 or above 18,000, here say 22,000, then the slope of the curve, or the population of fish, will decrease until it reaches the carrying capacity of the lake, which is the 18,000. We haven't talked about concavity yet, so we're going to do that in the next part of this, and then we'll come back to these graphs so we can answer these questions too. But I wanted to take just a minute to see how you could see why the graph is increasing as long as the population is between 0 and 18,000. And the function is decreasing if the population is greater than 18,000, and that would be a case like this. So if we go to find the second derivative, then d squared p over dt squared is equal to, and I'm going to use this form right here because then I don't have to use the product rule. So the derivative of 3p would be 3 dp dt minus the derivative of this would be 2 over 6,000 times p dp dt. And then we want to make a sign chart for that, so we're going to factor out a dp dt. And so I'd be left with 3. This 2 over 6,000 can become p over 3,000. and the dp dt is out here. So then if we make a sign chart for p double prime with p values down here, this second derivative function is 0 whenever dp dt is 0, and dp dt is 0 at these values. And it's 0 whenever this factor is 0. And you can see if you put a 9,000 in here, then 3 minus 9,000 over 3,000 would be 0. And so I can determine the concavity for each of these intervals. If the population is between 0 and 9,000, then that would be in this region. So dp dt would be positive. And if I substitute in, say, 5,000, then this 3 minus 5,000 over 3,000 would be positive. So I know that the solution to this differential equation would be concave up as long as the graph is between 0 and 9,000. And if I substitute in a value between 9,000 and 18,000, say 12,000, then this would be negative, and if I'm at 12,000, this is still positive, so dp dt is positive, but this factor would be negative, so the graph would be concave down. And if I put in a value greater than 18,000, dp dt is negative, and this would be negative, and so I get a negative times a negative, or concave up, positive and concave up. So if we go back to these graphs here, then what we just saw is that the concavity of this function is up until you get to 9,000, which would be about right here, and then concave down after that. So concave up, concave down between 0 and 18,000. So I don't know the time value, but I do know that at 9,000 that we have an inflection point. And on this graph, since the population is greater than 18,000, it's concave up for all values. And then this is kind of a funny case when the graph, this point is at 10,000, and the graph is concave up when the population is between 0 and 9,000, but that would be over here, so we end up just hitting the part of the curve where it's already concave down. So the inflection point would happen at negative time values. And so there is a situation when your logistic growth curve might be concave down for all values of time greater than 0, and that would just be if the initial population was already above the halfway point. We talked about last time how the inflection point is always at half of the carrying capacity, and that is shown here, that this came out to be 9,000 and the carrying capacity was 18,000. So this last question here is determine the intervals of p where p of t is concave up or concave down. So for this one, it's concave up from this area here. So it started at 4,000 and it was concave up until 9,000, and concave down from 9,000, and population never quite reaches 18,000. So I think the parentheses and brackets are correct here. Right at this point, it's concave up, and to the left and the right, it's definitely concave up. The graph is concave up if the second derivative is positive. The second derivative here would be 0, so I'm not including that point. And since the population never actually reaches 18,000, I think a parenthesis is best here. For this one, the graph is concave down starting at the given value, 10,000, and going to 18,000. And for this one, and that's it, it's only concave up here. We're not paying attention to this half because the time value, we're assuming the time value is greater than 0. And this is concave up at, for p-values as low as 18,000 and as high as 22,000. So this will be 18,000 to 22,000. And it is concave up at 22,000, so I'm going to put a hard bracket there. I don't think anybody would be bothering with the details of brackets and parentheses here, but I think that's correct as written. So just summing up, we were basically taking a second day to make sure you have the details of logistic differential equations and that you understand that in general, they are an increasing function, and they have an inflection point that's halfway between the carrying capacity and 0. But there are some special cases that don't model this exact behavior. That's usually concave up to the inflection point, concave down after. For time greater than 0, in this case, the graph is always concave down because the y value started off above the inflection point. And in some cases, the logistic situation is such that the whole curve is above the carrying capacity, in which case the graph would be decreasing and concave up as it reaches down to the carrying capacity. So I think that covers it. The homework is a handout, and I'll see you during a Zoom video.